Welcome to AI for Good, the leading, action-oriented, global and inclusive United Nations platform on AI. Organized by the International Telecommunication Union, the United Nations Agency for Digital Technologies, in partnership with 50+ UN sister organizations and co-convened with Switzerland. The goal of AI for Good is to unlock AI's potential to serve humanity. In today's AI for Good event, we are counting on you to use the live video wall feature to ask questions and post comments to help create an engaging discussion. We encourage you to stay until the end to chat, connect, ask questions, and network with our distinguished facilitators and world-class AI experts in the neural network. It is now time to kick off the session and welcome our first speaker. The floor is yours.
Thank you, Anna. Hello, everyone. Good morning, good afternoon, or good evening from me as well. My name is Guilherme Martinez Roura from the International Telecommunication Union, and it's a pleasure to welcome you all to today's AI for Good discovery event on frugal learning of robot manipulation skills. In this session, we will look at why robots, despite major advances in AI, still struggle with tasks that involve physical interaction. While they can outperform humans in strategic board games, they often find it difficult to carry out the simplest physical movements involved in these same tasks. Today's talk will introduce learning approaches that help robots acquire manipulation skills through imitation and self-refinement using only a handful of demonstrations or exploration trials. And we will hear how representations grounded in geometry, manifolds, implicit shape models, and distant fields can support a skill acquisition. This event is part of the AI and Robotics Discovery Series, which features expert talks on research and innovation in autonomous and intelligent systems, and how these technologies can help address pressing global challenges. And again, we have a very distinguished speaker with us today, but as always, we're counting on you, the audience, to really make this a very engaging session. So you are welcome to share your questions in the AI for Good neural network chat room, and we will take them during the Q&A. So without further ado, it's my pleasure to introduce our distinguished speaker, Sylvain Callinon. He is the Senior Research Scientist at the IDIAB Research Institute. Sylvain, the floor is yours.
Thank you very much, Guilherme, for the introduction, and thanks for the invitation. Yes, so I'm Sylvain Callinon. I come from an institute called IDIAP in the Swiss Alps in Martigny. It's a research institute specialized in AI and machine learning. When we say that, we might think of some rebranding of a research institute, but for us, we have been doing AI for more than 30 years because IDIAP was created in 1991. So we have seen several waves of AI and machine learning. So at IDIAP, we have this common theme of research being AI for different activities. And I created a group called Robot Learning and Interaction 12 years ago. And we are specialized in transfer of skills to robots, and in particular, manipulation skills. Our PhD students are also affiliated with EPFL, so we have a joint development plan with EPFL, but we are still like an independent research institute. For those of you who know PyTorch, which is used a lot for development in AI techniques and machine learning in general, PyTorch was before Torch, and Torch originates from IDIAP. So it's a way I like to describe our involvement into AI techniques. And in my group, we are interested in this skill transfer problem. So how to transfer manipulation skills to robots in an efficient way with user-friendly techniques. So ideally, we would like someone to demonstrate some task to the robot, and we would like the robot to reproduce this task. But obviously, it's not only a record and replay problem. We need instead to extract what are the essential features behind this demonstration in order to be able to generalize, meaning that we need to adapt what is being demonstrated to new objects. So if I'm teaching a robot how to carry a box, I would like to change the size of this box, and also potentially changing the robot itself. So really understanding what the movement means, what the task means, does it involve force, what kind of coordinate system we need. So we're interested in this skill transfer aspect. and possibly using a small amount of demonstration. And that will be my takeaway in this talk. Like I will show what learning encompasses. We know that nowadays learning is a lot about big data, but I want to show here that learning is also about small data. And I also want to emphasize that learning is more of a bilateral process. It's more of an interaction when it comes to robots and physical embodiment. When we are interacting with an AI that is actually a robot moving in the world and being affected by physics and in particular gravity. So it's more about an interaction. It's also about machine teaching. It can go in both ways. It can be active learning because the robot can also learn on its own and ask what needs to be learned. And it's also about the evolution of this learning process, what can be called curriculum learning. The challenge is also to combine different kinds of learning strategies in the same way as we acquire new skills by using not only a single learning strategy, but we use a variety of learning strategy. We might observe the others, we might try on our own, we might get some knowledge from some people and other knowledge from other people. So it means that as an interaction, it's probably like multiple interactions with different people and trying to understand what we can get from each of these demonstrations. And it's also about having the robot refining the task on its own. So how to combine reinforcement learning with imitation learning techniques, and how to orchestrate that in a fluent way, because we need to take into account what the robot knows currently about the task. We need to take into account the availability of the user and other aspects, meaning that we need to orchestrate these different learning strategies in a useful way. I like to see that as a scaffolding process. You know, scaffolds are used to build a house, and it's a metaphor that is also valid for skill transfer. Because at the beginning, when you construct a house, you need a lot of scaffolds. So you need a lot of support in order for the house to be constructed. But while the house is being constructed, the more you progress, the more you can remove the scaffolds. And ideally, you would like the house to stand on its own after the construction process. So I see the skill transfer process in the same way. At the beginning, you need the user to be here to really monitor what's happening and how to teach the robot what to do. But progressively, the robot can acquire expertise and get to know the task and doesn't require anymore some corrections from the users and can ideally do the task autonomously at the end. So we like to view learning as this scaffolding process. And the term that we like to use, and is the term of my presentation as well, we are talking about frugal learning. And here, frugality means two things. It means frugality in the amount of data that we need in order to train these systems. And in our group, we take, I would say, the extreme case where we are sometimes talking about just a few demonstrations, really like a dozen demonstrations, and understanding what we can do out of this tiny training set. And it's also frugality as in the sense of what needs to be learned. Because there is a big risk in robotics is that, robotics has so many components for control, perception, planning. You have all of these challenges requiring to have a lot of know-how. And it's very tempting to discard this know-how and instead use data to do the task. So trying to make it really as end-to-end learning. But in our group, we believe that there is a lot of prior knowledge that you can inject to the system so that data is still used, but data is used only when we cannot model what the task is, or when we don't have a priori information about what the task is. If we don't know the physical model, then we will do it as a data learning process. So we try to balance really model-based optimization together with data-driven techniques using learning components. And we do that for manipulation skills. So our main interest is to transfer manipulation skills to robots. We are interested in various forms of manipulation. Prehensile manipulation, meaning that we need to grab objects. And here you can see examples where we don't want to grab objects only with the gripper of the robot, but sometimes we would like to use the whole arm. If you carry a large box, will not use your fingers, will you actually use your forearms in order to have the box standing on your forearms. It's very important for humanoid robots because humanoid robots, you cannot put very complicated hands. They would be too heavy. So you also need to use really like the whole body of the robot if you want to provide manipulation capability to these new humanoid platforms. So here we are studying this with bimanual tasks. We are using robots in our lab that are compliant robots, torque control robot. And here we test different ways of using the whole body as a geometric way of describing what kind of contact point we can use to solve the task. Then we also study the problem of using tools. If we don't want to use the gripper, we can still use tools that the robot can grab. And in many applications, you have a diversity of tools that you might want to use. And here, these tools can be used to simplify the work of the robot. So here in this example, I provide some kind of ratchet that the robot can use. And if the objects are too far away, then the robot can use this tool in order to bring them closer. So that's for prehensile manipulation. But now we have also a lot of non-prehensile manipulation skills. These are all the skills involving pushing or pulling objects. And here, these tasks are important. We do quite a lot of work by pushing and pulling objects on a table, typically. Like if we have large boxes that we need to align, then it's likely that we will exploit the environment and we will not put the box directly where it needs to be. We will put it first closer to us and then we'll slide it because it's much easier to do. We don't need to take too much energy to do this. So pushing, pulling is important for that. It's also important for perception because you can simplify the scene if you are separating objects that would be stacked somewhere. It's also simplifying the separation of objects in order to grasp them. So if they are better separated, we can grasp them in an easier way. And it's also more generically useful to be able to reorient objects. So if we now think of exploiting the environment, then we can also think of tasks such as pivoting object using the environment in order to manipulate dexterously these objects. Another example of non-prehensile manipulation is this Aero-Kit challenge in which we participated. And here it's involving more eating movement and also like strategies about how to bounce the pallet on the wall in order to win the game. So these are examples of non-prehensile manipulation skills. Now we are also involved in projects focusing on very precise manipulation. Typically with watch manufacturing and these different kind of industries that require very precise movement to be done. And often we have platforms that are very expensive if we want this precision. What we demonstrated in this task is that we don't necessarily need to use expensive robots. We can actually use cobots that are less precise and available more easily on the market, and use instead a wise way of correcting for the imprecision that these platforms have. And this process is requiring some active perception so that the system is correcting online by perceiving what are the offset in what we want to do. And it's typically what we do on our own, like if you try to do a task blindly, you might not do it correctly, but if you have the visual feedback, you will correct your movement. And here we did the same with this platform, and we could demonstrate that with a wise way of sensing the environment, we could achieve this very precise task of using like a needle head and using a string, and then we could actually put the string in the needle head. Why? If we look at the data sheet of the robot, we are not supposed to do that. Like it goes like over the precision of this robot. But if we have this local correction, we could achieve this. Now let me give you a last example to show what we do in our lab. So that's the important point I would like to convey first. We are also working on teleoperation. And teleoperation is, in my view, human-robot collaboration. Like we have the robot doing some part of the task, the user doing some other part of the task. So teleoperation is just distinct by the fact that the user is usually away from the robot. And the robot is working at remote places that can either be dangerous or where you want to have the robot like being deployed in a fast way or maybe inaccessible places, such as here in this example in the bottom of the ocean floors. And here what we did in this project was it was a large European project, and there was a teleoperation center. And the idea was to teleoperate a robot to do some valve turning, like very, very deep in water. And we had this slow communication process because we cannot communicate with the robot in the middle of the ocean in an easy way from a teleoperation center. So here we had to bring some form of, I would say, intelligent correction for the robot to be able to handle situations locally. And in this example, what the robot was doing is to automatically correct for the perturbations by transferring only the higher level information. So the user was in the teleoperation center, showing what to do in a virtual reality setup. And on the other side, once we were getting data from the user and the robot was in some way like correcting its plan, but locally it could adapt very fast to perturbation. And it could always, for example, align its hand so that the valve could be turned efficiently. And before doing this kind of projects, we need often to work on the algorithms in a simpler setup. On the last video on this slide, we will show how we did this kind of complicated setup in our case. So what we did to replicate this kind of scenario was to use two robots. One was used as an input device, and the other robot was used as the output. Here in our lab, these two robots are close by, but in reality, one could be very far away. And here the valves were placed differently on the left side or on the right side. And as you can see on the video, there is this automatic adaptation that the user doesn't need to care about the positioning of the valve on the other side, but can fluently demonstrate, here in this case kinesthetically, so by really grabbing the arm of the robot to demonstrate what to do. And without caring about the robot on the other side, we could have this smooth mapping of coordinate systems. So even if the valves are placed differently, we have this mapping allowing us to reproduce the task efficiently. So that's an overview about what kind of task we are working on. And now in the rest of this presentation, I will show you 3 different techniques that we use to do these different kind of manipulation tasks. So it's like some kind of highlight to give you some ideas about what do we have as research components behind and what kind of models we are considering. And I will propose 3 different models. One is called ergodic control. The other one is called tensor networks. And the final one will be related to geometry. So the first is about tracking a distribution instead of tracking a point. Indeed, in robotics, the task is most of the time formulated as a point that we would like to reach. Like we have a target, and we ask our robot to reach for this target. Now, ergodic control, instead, is specifying the target as a full distribution, meaning that there is an area that we would like to cover efficiently. So we would like to move within this area. And doing this, it means like we would like to search for something that would be hidden or that where we don't know the exact location. And we would like to explore by moving around this distribution in order to determine where are the objects located or where is the object we want to find. Think of the example of finding our keys in a living room. My argument is that ergodic search is a much more natural way of searching for your keys in your living room. Like you have some kind of initial distribution that could be the usual locations where you drop your keys. It can also be flat surfaces because it's easier to put keys on a flat surface. So you have some kind of distribution that is telling you, okay, these are the areas where I believe the keys could be. Then your goal is often to find your keys as fast as possible. So the pattern search that you see on the right side of the screen is not ideal in this case, because a pattern search means that you have a scan of the environment that can be very slow. Like if you do the experiment many times, then on average, it will be much slower to do this kind of pattern search rather than an ergodic search. And the reason is that the ergodic search is specifying the problem as from low resolution to high resolution. So if you want, it's like trying to solve the problem in a very blurry manner at the beginning. So it's like, I would say, like roughly scanning for the keys in the room. And if you don't find the keys like that, then you will look at more details. If you don't find your keys, you will look at even more details. And you will do a process that is really like exploiting the different spectral bands. So it's like really something that has a frequency problem where we need to take into account this frequential aspect and to view the task as something from very blurry on the low resolution task up to a very high resolution task. And this is exactly what ergon control is doing. And here, like on average, you will find the keys much faster if you use these techniques. So for robotics, we use that for insertion tasks. In insertion tasks, you have the same problem. Like if you have a sensor with low resolution, you will not know exactly where is the entry point that you would like to reach. So you can specify that as a distribution, but you don't know exactly where it is. Same thing with the gripper. The component that you are holding in the gripper, you might not know exactly where it is. You might also have an inexpensive robot that maybe is not precise enough to understand exactly where it is located in space. So because of this, using ergodic control will generate some exploration behavior that will allow the robot to fulfill this task, even if we don't know exactly where are the point we would like to reach. So that's the first example of application. Another example is to exploit this as a coverage problem. Like initially, it's really formulated as a control problem where we would like to cover for some areas. Here, these areas in this example are spots on dishes that we would like to wash. Here in this lab setup, it's not dishes being dirty with food, it's just like a marker being used to play with the robot. And the goal of the robot is to erase these red marks that we are putting on the different kitchenware. So here it's to also demonstrate that this ergodic control problem is not only in a plane or in 3D, it can also be on point cloud. And here in this task, we are using also vision to determine what's the shape of this different kitchenware. And we don't have a priori model about this, and we have the robot being autonomous at washing these dishes. So that's the first example of a technique that we are using in our task. Then the second one is what we call tensor networks. Of course, many of you are familiar with neural networks, and there are many different kinds of structures that you can consider for neural networks. Tensor networks is a bit less known. It's known a lot in the field of physics. It's also like a processing pipeline. It's also like about trying to extract the essential information out of the data. But it's a technique that works much better if we have small amount of data, which is the case when we are talking about learning from demonstration, where the user is directly showing to the robot what to do. We often have much smaller data sets compared to machine learning tasks that would involve images or text. So for us, tensor network is an important processing pipeline. And there are like really diverse structures that exist. And in our work, we use a lot the tensor trains, which is one model among others. But there are a lot of literature in research that is like trying to see what this structure can do for optimization problems, for reinforcement learning problems, or for supervised machine learning. So to give you some kind of idea about what it is, the goal is to model a reward function. Like a reward function is telling you if the robot has succeeded or not in the task. And the decision variables will be either some environment variables that will describe the scene, like for example, the locations of objects in the environment. And you will have some policy variables that are like what the robot has to do. Like if the object is here, how the robot should move. So it can be like actions, it can be plans, it can be trajectories. And if we have a model of this score, like to know how much the robot has succeeded, then we can use a sampling technique so that in a given situation, so if I'm along this line, I would like a system being able to generate policy variables that would give high score, so high reward. And we can do that by thinking of conditional probability, so by modeling this distribution in a probabilistic way, and ergodic on the tensor train will allow us to do this. So you can think of it as a decomposition of the variables. Like we try to find a low rank decomposition that would allow us to represent this distribution with fewer parameters than the original distribution. Here I'm giving an example with rank 2 decomposition or rank 1 decomposition. So that would be linear algebra if I'm representing it like that. Now, what we use is a bit different than if you know about principal component analysis or singular value decomposition. What we use behind tensor train is a bit different because it's called a skeleton decomposition that is actually using these tall matrices are actually composed of the original data. And the main novelty compared to this two-dimensional problem is that it's working with many decision variables. So we don't need to stick to linear algebra where we have vector and matrices. We can consider problems that are multilinear algebra where we have many decision variables and we still use a similar pipeline where we have this tensor data being represented as a train of tensor cores. And this problem formulation is allowing us to learn a task in only a couple of hours. So here I'm talking for very simple tasks, it can be 10 minutes. For a robotics problem, it's usually between 1 up to 4 hours. But we are not talking about days or weeks of computation here. And the retrieval part, so to sample for solutions, here it's extremely fast. So the sampling part of this problem takes from 1 millisecond up to 10 milliseconds. Now I will show you this example as generative mechanism. So here I'm really showing samples in these animations. It's often samples where we need to reach for an object and we need also to avoid obstacles in an environment. If I may be taking the example in the central video, here what we have as input is a picking location and a placing location. And as output, what we generate is this full motion that will grab the object and put it on another place on the shelf. So we need to avoid the shelf as an obstacle. And here you see multiple robots because we have multiple ways to solve this task. And here these are just samples of different ways of doing the task. And these samples can be generated in parallel. So it's really like a fast process to generate solutions. So in our work, we have been extending this to various like more elaborated problems, but here I wanted to give you a flavor about what this is. We use that for model predictive control, for dynamic programming, and also for learning problem involving Monte Carlo tree search. So all of these work are using the same core processing pipeline of a tensor networks. And this brings me to the last part of my presentation, that will be about discussing the role of geometry as inductive bias to a learning problem. And here I will show different ways of treating geometry. So the first way is to use what is called geometric algebra. Geometric algebra is an approach that is allowing us to treat points in the same way as full coordinate system, as rigid body motion, but also planes, lines, spheres, and circles. So we have these basic geometric shapes. And the advantage of using geometric algebra is that when we write a function, so when we make some computer code, which can be, for example, interpolating the interpolation between two objects. Like if I have a point and I would like to reach another point, then I can write an interpolation function that will give me the list of intermediary points to move from one point to another. With geometric algebra, what is nice is we can write this function and then change the object. So we can then call this function with other objects. So I can call the function with two lines, and I will have a smooth interpolation between two lines. I can even put different objects, so I can make like morphing between planes and spheres, which would like squash a sphere to make it as a plane. And it's not only for interpolation, so it's really like each time we write a function, it will be valid for these different objects. And the reason why we care about these objects in robotics is that they can represent constraints. We often have constraints being represented in this form. Typically, if we would like a robot manipulator to stay in a plane, then we can think of the problem as reaching a plane, like we would like to reach for a plane. If we think of maintaining a distance to a specific point in the environment, it means we need to stay on the surface of a sphere, because the sphere will have a given radius, and if we want to stay at a given radius to the center of this sphere, then it's the same as tracking a sphere. And we have a lot of these constraints that can be formulated geometrically in this sense. It can also involve the user, so it can also be constraints regarding human-robot collaboration. It can involve multiple contact points, and it's geometric object that can also be used for control. Here on the right side, you see one of our latest experiments where we use a simple 3D mouse input as a way to control a sphere. And here what it means, controlling a sphere, it means like moving it, so translating the sphere in all three directions, but also changing the radius of the sphere. And if we use that as an object, as a geometric object, then it means for a robot that you will have the fingertips of the robot. Here we need 4 fingertips that will automatically close. And it's a way for us to coordinate multiple limbs, like multiple fingers in this case, by using a simple geometric object. So that's one of the first techniques that we can use in geometry. But there are many other ways of representing shapes in the environment. So sometimes we need very simple geometric shapes, sometimes we need more elaborated ones. So it's why in our work we are looking at like various solutions that we can use to cover the different range of geometric problems that we have in robotics. So here I'm just showing a few examples of representations of shapes used in robotics. We can use meshes, we can use point clouds, we can use shape primitives, occupancy grid, or distance function. And a large part of our work is focusing on this last one. It's like a distance to an object. So it can be used to represent shapes implicitly. It can be objects that the robot needs to manipulate. In reality, we don't care only about the distance function. We care also about the derivatives of this distance function, because the derivatives will tell us where to go if we would like to touch the object, or also where to go if we would like to avoid this object. For example, if you have you are computing a path and you see that the path is coming inside of your object, then you would like to know this distance and the direction so that you can change your path so that you don't enter into the object. So that's valid for objects. That's also valid for the robot itself. The examples I was showing with the bimanual task with whole body manipulation was using this form of distance field. It can be used for planning and control techniques that are directly at the joint angle level, so working directly at the level of the articulations of the robot. And it can also be used as a way to represent trajectories in an implicit manner. So here the idea is that we start from a trajectory, which can be a demonstrated trajectory, or a trajectory being found by an optimal control technique, typically. And what we do is to transform this trajectory into a distance field. And we use the derivatives of this distance field to generate some policy that is telling to the robot what to do when being faced with perturbation. So with a flow field like this, like if you move the robot away, then the robot will know what to do because it's generating an autonomous system. And there are many other ways of exploiting these techniques as implicit models representing trajectories. And we are currently investigating what it means to do that in latent spaces. So using neural networks to find a latent space, having trajectories in this latent space being converted into autonomous system, and we demonstrated that we could beat several benchmarks if we were treating the problem as trajectories instead of policies. So that's one of the possible aspects of thinking of objects as implicit distance functions. But we can go one step further. And this is what is being investigated in this work, where the goal here was to extend the notion of distance to a full coordinate system that would move along the surface of an object. So the basic idea is the following. You take an initial coordinate system and you slide it along the shape of your object, and then you slide it in the whole volume surrounding the object. And if this change is smooth enough, it's generating a local coordinate system that is very meaningful for manipulation tasks because it's describing the problem in a very intuitive way. For example, if you want to stay at a given distance to an object, then it just means that in this smoothly varying local coordinate system, it means that one of the decision variable is constant. So the z direction will stay constant. And we could demonstrate in this work that with this kind of representation, we could first have a representation that is valid for control planning and learning problems, but also that we could transfer skills across different objects. So it means here that if we have demonstrations about peeling of a cucumber, then it's very easy to take this demonstration and to apply it to a different object without retraining. So it's really like zero-shot learning in the sense that if it learns on one, then it can replicate on another by using this smart encoding about what the task is as an object-centric view of the actions. And we demonstrated that also with cutting, with palpation, and we are currently conducting also like other research exploiting these techniques. So as a summary of what I presented today, so first I showed how ergodic control can be used as a way to cope with uncertainty. And I gave the example of uncertainty coming from the sensors, from the actuators, or from the grippers. And when we're using ergodic control, the user can still be here. So it can be like human-guided learning, but the role of the user is to provide a distribution. So in the example with insertion tasks, here the user was demonstrating to the robot the range of variations that is expected. And then during reproduction, the robot will cover this range of variations. So even if the task or the situation is not exactly the same, this range of variations will be exploited to adapt the skill to new situation. Then in the second part, I showed how tensor trains can be used for human-in-the-loop and frugal learning technique. Tensor train is one model as part of the more general category of tensor networks. And tensor networks is a good complement of neural network, especially when we have smaller amount of data to be considered. And lastly, I showed the advantages of geometry for robust control and planning. And I showed the importance of implicit shape representations and also to have object-centric controllers. Here are the persons behind this. So I showed here the current group members on the left, but we also have like R&D engineers who contributed to this work and alumni who were all at IDIAP. And some of the work that I showed today were also like part of this work.
Thank you, Sylvain, for this amazing presentation. So now we would really love to hear from our audience. So if you have any questions, please share them in the AI for Good neural network chat room. And while we wait, I would like to start with a few questions following your presentation.
Yeah, and if you agree, for the questions, for the Q&A, I will just run this video. I will not talk about it, but I will just run the video to entertain people while answering the question.
Okay,
Yes,
okay,
please.
that's great. So I mean, you explained that frugality means using both small data sets and learning only that what truly needs to be learned. And I would like to ask you how you decide which parts of a manipulation task should rely on prior models and which should be left to data-driven refinement.
Yeah, thank you very much for the question. It's an important question, and it's not yeah, it's quite hard to answer. So often first we have problems that are sometimes wrongly formulated.
Yeah,
For example, if we know already how to solve a problem, then we don't want to learn it. Even if it could be, I would say, an exercise to see if our system could learn something that we already know,
yeah,
then we could do it, but it's not useful. So I would advocate to really try to see in robotics what we can do without learning, and at some point we will need learning,
okay,
but not making, like not trying to reverse engineer something that we already know.
okay,
And sometimes what we already know, sometimes it's related to physics. So here, for example, I'm encouraging to use physics-informed neural network. And what I presented with geometry, it's part of these models, like geometry is part of physics, in the sense that if we have some kind of geometric knowledge, then it's better to use it. And the same for physics more broadly speaking. If we know about gravity, we don't want to have the robot learning about
yeah.
gravity. So it's why I think that we need to be careful about what needs to be learned, and then to care also about the number of, like the amount of data that we need to do this.
Out of data. Okay. So and I think I mean you use the scaffolding metaphor. So how do you see this approach as scaling when multiple users with different teaching styles interact with the robot?
Yes, that's another excellent question. So here we don't really have solution. It's more that we are aware that we don't use as efficiently as we could these different learning strategies. Typically, what will happen in research is that we will have one group specialized in reinforcement learning, but only doing reinforcement learning. We will have one group specialized in learning from demonstration, but only doing this part. We will have maybe one group considering only high-level learning, something really like at symbolic level, which is also like another important learning aspect. Some other group will see learning as something that is very low level by thinking of this as policies, as controllers. And in reality, we need the mix of all of this. Like we need like to combine these different techniques. And the problem itself of combining that is not easy, because some techniques involve the user, some techniques don't. And if you really want to take all of these factors into account, then it's another kind of meta-learning problem, where we need to consider what the robot needs, what the user needs, how often the task is changing, how often the environment is changing. So there are like a lot of aspects to consider. So I was in some way like trying to promote techniques that would, I would say, mimic the way we are learning skills and acquiring skills. And since we use multiple learning strategies, then I guess our robots could also similarly use multiple learning strategies.
Wait, I was muted. So we have some questions from the audience. So one of them is how memory works for continuous learning. Are there any breakthroughs in memory recall that are exciting for your team?
Yes, definitely. You know, we worked on a European project called Memory of Motion. And it was a large project with many partners. And the research topic was exactly about that. It was about understanding and making models to understand better how to efficiently use a memory. And in this case, it was a memory of motion in the sense that currently we have too many things being thrown away. You know, like we have the robot learning something, and then we throw away this knowledge. And it happens, unfortunately, too frequently where we throw away something that we already know, and then we learn again because we have changed too many things. Maybe we have changed the models. Maybe the task is involving various elements that doesn't allow us to reuse what the robot already knows. So in this project, we were like trying to see, okay, how to build a memory that is in some way compact enough so that we could have a robot that doesn't need to forget about what it knows, but that the robot could reuse efficiently what is stored in this memory. So it's really something as a compressed model. It's not really storing as we store files. So it's not only about compressing files. It's more elaborated than this. And it's also like using prior knowledge about what we know about movement, about physics, and about different geometric aspects that we can put in the system.
All right. So we have another question on the like different like promising applications for ergodic control. I mean, you mentioned in insertion and coverage tasks. Are there other tasks that could be included in this ergodic control that you were mentioning?
Yes, thanks for the question. Definitely. One that I didn't talk about, but that I believe is very important is all of the search and rescue aspect.
Yeah.
And also surveillance, you know, like all of the, I would say, mobile robot techniques. Here in this talk, since we are specialized in manipulation skills, I focused on this kind of applications. But in reality, ergodic control is used a lot with aerial vehicles, with mobile robots. And here, the distribution that you provide, it's really like a map. You know, like if it's, for example, there is if there is like an aerial robot that needs to cover some area, then you give this as the distribution, and then you will have an efficient search. So for search and rescue, it means you can have robots finding that will find what they need to find in a faster way than if they do this kind of very like pattern search that can be quite slow.
Okay, so I would like to ask about the tensor networks that allow learning from very small data sets. What developments do you expect to help bring these techniques into wider use in robotics?
So, yeah, that's an excellent question. So it's a technique that is not really new. Like in physics, it was called matrix product state. So there was actually a different name. And then mathematicians in some way rediscovered this technique, and they were using the term tensor train and tensor network to talk about this. I can see clearly that there is a trend of looking at these techniques more and more for, I would say, broadly speaking, computer science, but also for optimization problems. So we see more and more papers talking about tensor train, not only to compress data, but really tensor train for reinforcement learning, tensor train for optimization, tensor train for supervised learning. So we see more and more of these techniques, and our work is also in line with this, where we see that it's a processing pipeline that can also benefit other applications that have nothing to do with physics.
Okay, well, thanks for this, Sylvain. So we have more questions coming from the audience. So one of our attendees states that human memory is notoriously porous, and I've read a lot about how it's easy to inject a human being with false memories of different things that maybe he did not or she did not commit. So the attendee is curious about security in embodied agents and how they might stay cognitively sovereign.
It's an important problem. Well, you know, like we need to talk about that quite seriously. When we have embodied agents, so what we can do out of these out of this in terms of security is important, like for many different aspects, because we have a physical platform. So it can be safety as, like a humanoid falling, for example, and then it can be safety as way to use this platform as like as exploiting this platform in bad way. So I think it's something important, and I guess that the more interpretable the model is, the best we can monitor what the system has learned, what it will do. Like we can put in some way some bounds about what we expect the system to do. We cannot always have interpretable models, but if we can have at least some part of it, the one that are related to control as interpretable model, then I believe it's reducing the risks. And here, all of the techniques I showed, we have this interpretability aspect.
Yeah. Okay, so I'm gonna maybe like move to unless there are more questions from the audience, but I would like to ask you about the non-prehensile manipulation and environmental exploitation. What are the key steps towards enabling these robots to discover such strategies fully autonomously?
So I guess first, do we really need to make this like fully autonomous? So I would say what we don't want is to have something like showing too many times to the robot something that would be similar.
Yeah.
So, like if we have a system where the user is feeling that it's useless to show something, it means maybe the system was not crafted in a good way. But if it can rely on a small amount of demonstration, and if it can speed up this reinforcement learning problem, then I believe it's a best use of like human guidance versus robot learning autonomously. So I guess it's really like a mix about this. Like it's like having a robot understanding if it can use maybe prior knowledge, if it can use something that it has previously learned. It's also like trying to, I would say, to gauge like how much it would gain from a demonstration. Because, like if you have like, if the robot could learn something with a 5 second of demonstrations of someone, then it's better than having to spend 1 day trying to learn on its own. But sometimes it's the opposite. So sometimes a human demonstration can be very costly, while the robot could simulate the task and learn it in a very easy way. So I think it's really like about balancing what's the pros and cons of having human-guided technique versus self-refinement technique. And also, like, ideally what you would like is that the robot doesn't stop the task. So we have also like, we are considering also problems where you have the robot doing the task, but refining the task while doing it. So it's also like something that is a hot topic of research. It's to say, do you really need to stop the machine when it's learning, or can you learn while doing?
Yeah. Okay, so we have, thanks for this, Sylvain. We have one last question from the audience. So are there any safeguards for robots learning by imitation in difficult situations, in situations that would be, for example, unlawful, or like that guardrails would be needed? Is there anything to prevent the learning by imitation in, I would say, for not good, like to really support for good applications only in this learning process by imitation?
So I think it's a bit similar to the previous question regarding the what kind of models are being used.
Yeah.
And here, if you have models that are like interpretable and that can, I would say, separate these different parts, then you have much more control about what can be done, and you can put safeguard about what can be like either executed or even demonstrated, or what can be. It can also be, like if we think of robots that are like powerful platforms, it's also like about limiting what kind of acceleration we have, how swiftly can a robot react to something happening, how much force also is being used. Like we have a lot of tasks that are physical human-robot collaboration. And here it's very important to have interpretable models so that we know exactly what kind of force will be applied when interacting with the person. So I think, at least for what we do, it's more about providing technology that is allowing to put this safeguard. But then, in general, to deploy this platform, then here it needs to be a discussion with other people who are actually specialized in this domain. And I think this kind of technique, like technologically speaking, it will help to have like other people deciding after by knowing the safety aspect or specialists in the safety aspect to know how to best exploit these technologies.
No, excellent for this. So I think, Sylvain, we would like to thank you and everyone who joined the session today for all this, really to go deeper into the frugal learning in robotics, and especially for robot manipulation. We as well appreciate the active participation from the audience, and we encourage the AI for Good to explore the AI for Good program online, where you will find more upcoming sessions on robotics, learning from demonstration, embodied intelligence, and related topics. And this brings us to the end of today's AI for Good Discovery event. And I will hand now the floor back to Anna for the closing information. And again, Sylvain, thank you very much. And
thank you very much.
I hope to see you in person soon in 2026 here in Geneva at the Global Summit. Thank you very much.
Thanks again.
Bye-bye.
Thank you for participating in today's AI for Good session. We hope you've learnt something new, innovative, and engaging in today's event. We now encourage you to continue the conversation on the live video wall in the neural network. Here you can ask questions, like and comment, share links, complete the poll, connect with interesting profiles, or speak one-on-one using the chat and video function. We invite you to explore the lobby, try the smart matching quiz, visit the virtual exhibits, poster boards, the e-shop, and build your personalized AI for Good program. Let's shape the future of AI for Good.